is identical particles and in identical particles we have quantum particles. Okay, I told you when I introduced you with the syllabus. So quantum particle can be divided into two categories. One that follow Pauli's exclusion principle is called fermions, and the another one that do not follow Pauli's exclusion principle is bosons. Okay, fermions and bosons. So this will follow Pauli's exclusion principle, and it will have spin like this, 1 by 2, 3 by 2, like that, and it will not follow no Pauli's exclusion principle, and it will have spin like 0, 1, 2, like that. Okay, so this is the fundamental difference. So we have a separate distribution function obviously for fermions, and we will have separate distribution function for bosons. Okay, so let us discuss them one by one. So the first one is, this is clear? So अगर शुरुआत करते हैं fermions से, let us begin with fermions. So fermions will follow Fermi-Dirac statistics. Okay, they will follow Fermi-Dirac statistics. So what are the things that I will consider here? It will be a quantum particle. Okay, so quantum mechanics is applicable, and the particle will be identical but indistinguishable. Particles will be identical but indistinguishable, and the distance between the two particles will be much smaller than thermal de Broglie wavelength. So that means there will be overlapping of the wave function. Then only quantum effects are important. So like you have two particles like this. This is suppose distance between them is 2, and some wavelength is associated to with this, and this is wavelength associated to this. So these wavelengths, they will overlap. So that's why the quantum effects will become important. Okay, the spin of such particles will be half or 3 by 2. These will be the spin of such particles. So for example, you have electrons, you have protons, you have positrons, neutrons. Okay, electrons, protons, so they have spin half. Okay, now these particles following the Fermi-Dirac statistics, they are related, they are written in the form of, their states are written in the form of antisymmetric wave function. Antisymmetric wave function. So this you will read in quantum mechanics, that overlap of two wave functions can be symmetric and can be antisymmetric. So the antisymmetric ones will be used to represent the fermion, and the symmetric wave functions are used to represent the bosons. Okay. Then they will follow Pauli's exclusion principle. Exclusion principle. What is that? One particle, one particle, one quantum state. One quantum state. So एक particle और एक quantum state. So that means if you have one quantum state, only one particle can be there. This is Pauli's exclusion principle. Okay. So because of this, the whole world around us, the solid world around us is made. Because one particle, one quantum state means the next electron or next proton has to go into another state. So that's why एक level से दूसरे level, तीसरे level, चौथे level, इस तरीके से structure of the energy levels are formed, and hence we have the solid state structures around us. Okay. So if all particle will fall into one energy levels like in bosons, then your this solid structure will be gone. So the solid structure is because of the Pauli's exclusion principle. Okay. So यहाँ तक कोई, you have any doubt up to here?
Sir, what is antisymmetric wave function?
So this you must discuss in quantum mechanics, how to write. So suppose there are states, yeah, there are two particles, 1 and 2, and psi 1 is associated with the first and psi 2 is associated with the second. So how antisymmetric wave functions are written? बीच में माइनस साइन आता है, राइट? और बोसॉन में प्लस आता है, तो दिस यू मस्ट डिस्कस इन क्वांटम मैकेनिक्स. मैंने जस्ट इंफॉर्मेशन के लिए बता दिया. ओके.
Yes. The third point at D is much smaller than.
हाँ, तो दो पार्टिकल्स हैं, 1 और 2, इनके बीच की डिस्टेंस d है.
Yes sir.
तो अगर d बहुत बड़ा है और सपोज ये इनसे एसोसिएटेड वेव फंक्शन है, तो यू डोंट नीड क्वांटम मैकेनिक्स.
Yes sir.
ठीक है. एनी अदर थिंग? Video is lagging. Beulah, is it lagging for Beulah or it is lagging for everyone? Indistinguishable means particles will be written like this, A. Okay? Every particle will be same. You can't distinguish. Video lag कर रहा है क्या भाई?
No, sir.
No, sir.
Okay. Tell me, ये clear हो रहा है? Yes, Meenal, is this okay? This much is okay?
Yes, sir.
Kanchan,
Yes, sir.
clear है इतना ना? Okay. तो इतना समझने के बाद, हाँ जी,
Sir, can you explain third point, sir?
हाँ, which point?
Third point, D
Point?
less than less. Third point, sir. D less than lambda.
So suppose this is particle 1 and this is particle 2. Okay. And suppose there is some wavelength, de Broglie wavelength associated with thermal de Broglie wavelength associated with particle 1. There is also thermal de Broglie wavelength associated. If D is much greater than lambda t, then two particles don't need quantum consideration. You can treat them classically. But if D is smaller, and the wavelengths overlap, then quantum effects become important. Okay?
Okay.
Off your mic. Immediately after asking question, please off your mic, okay? So that इस तरीके का डिस्टरबेंस मेरे माइक से तो नहीं आता भाई?
No, sir.
आप लोग का माइक ऑन होता है तो देयर इज लॉट ऑफ डिस्टरबेंस. तो ऐसा लगातार मेरे माइक से तो कोई नॉइज नहीं सुनाई देती.
नहीं, sir.
ओके ओके बिकॉज दीज आर नॉइज फ्री हेडफोन्स. हाँ, सो अब जो सबसे इंपॉर्टेंट बात हो जाती है, यू विल सॉल्व previous year questions of especially TIFR. You all must do questions from TIFR. Okay, maybe in one or two questions we will get stuck, but 99.99% we will be able to solve. So suppose you want to write partition functions, so for that you will write all type of microstates. So suppose let me give you that suppose this is the energy levels and fermions is given. 2 fermions are given. Okay, 2 fermions are given. And we have to write the partition function, and this is energy 0, this is E. Okay, please see this. ध्यान से देखना. So this is fermion. ये क्या है? Fermions. So they can be like this, they can be like this, and they can be like this. Any other thing that we can do? Any other distribution that you can do?
No, sir.
No, sir.
No. So what is the energy here? E. What is energy here?
2E.
2E. What is energy here?
E.
E. So now you have energy levels. Because of the two particles, energy levels are formed, E and 2E. Am I right? So if you write the partition function, it will become 2 times e to the power minus beta e plus e to the power minus 2 beta e. Am I right? Yes.
Yes, sir.
Sir.
So,
And what will be the average energy? You can calculate from the partition function. And obviously, average energy will be what? E और 2E. So E से थोड़ी बड़ी होगी और 2E से छोटी होगी. You can calculate it using partition function. You know na the formula? U is equal to minus 1 by Z del Z by
Del beta.
del beta. This is what is called average energy. Okay. So ये समझ आ गया सबको? Fermions का distribution. इस type के बहुत बार you have been asked the questions that these are the energy levels and there are two parts. Please don't use this formula here. Don't do that. You calculate it for one particle. Why? Anybody can tell?
because their number of particles are not large.
So for this n should be large. Okay. So if 1 or 2 particles, 3 particles are given, you have to write all the microstates and then you have to write the function. Okay. And if you know the formula for, if you know if you want to calculate the number of ways in which the particles can be arranged, suppose there are many energy levels like this, And in every energy level, suppose this is Ni, and this is the situation. There are many energy levels, and there are different number of particles present in different energy levels. Okay, and these are the degeneracies that are present. Then the number of ways in which these particles can be arranged is given by omega I is equal to gi factorial upon gi minus ni factorial into ni factorial. This is the formula. Okay, so this you can use if directly number of particles are given. For example, suppose this is the situation. Okay, this is the situation. Here one particle, here two particle is given, and this is n1, this is n2. Number of particles are given, and you have been asked in how many number of ways these fermions can be arranged. So you will write omega is equal to, please see the formula, 1 factorial upon 1 minus 1 factorial into 1 factorial into, this is 3 factorial upon 3 minus 2 factorial into 2 factorial. So this is the answer. समझ आया? So this is
Sir, here particles are the fermions, no? Means we have considered.
कंचन थोड़ा तो सोचा करो क्या क्वेश्चन पूछते हो. क्या टॉपिक डिस्कस हो रहा है भाई?
Fermions only, sorry sir.
तो मैं यहाँ पे बोसॉन ले लूंगा जब फर्मियन डिस्कस कर रहा हूँ. ये तो मतलब कॉमन सेंस तो यूज करना पड़ेगा. वी हैव टू यूज कॉमन सेंस. व्हाट आई एम डिस्कसिंग, टेल मी.
Fermions only, sorry sir.
So these are apples which have to be arranged. हैं?
Yes sir.
Are these are apples? One apple and two apple. Are you are discussing fermions, so these will be fermions, obviously. Yes or no?
Yes sir.
Okay. So what is this? Omega? Omega कितना आएगा? This is how much?
Three.
3. 3 ways. And if you optimize it, that means you calculate S is equal to KB ln omega and then maximize it with respect to Ni, like we did in Maxwell-Boltzmann, then you will get the formula which is called Fermi-Dirac distribution. Direct कई बार पूछा गया है. Fe, which is Ni by Gi, that means number of particles per unit quantum state, and this is given by 1 upon A e to the power beta e and plus 1. And what is A? A is e to the power alpha. Okay? E to the power alpha. And you can write e to the power alpha as e to the power minus beta mu. So these are, A is called fugacity and alpha is the same alpha that we calculate in Maxwell-Boltzmann, and mu is chemical potential. So you remember this formula. How you will put it? F of E will be, कैसे लिखेंगे बताओ? 1 upon e to the power beta e minus mu plus k. Let me write it like this. If k is 0, it is Maxwell-Boltzmann. If k is 1, it is Fermi-Dirac. If k is minus 1, it is Bose-Einstein. समझ आया? ये previous year question है. From this, you can calculate this by optimizing omega with respect to Ni. So you write S is equal to KB ln omega. So or you write just ln omega and optimize it with respect to Ni, you will get Fe. Why you can optimize? Because at equilibrium, entropy is maximum. So KB ln omega will be also maximum. And for maxima minima, we know how to handle it. Okay. So, but this we should remember because we have to use it directly. तो इसलिए हमें ये पता होना चाहिए. इसको degeneracy parameter बोलते हैं. A is known as degeneracy parameter. Is it okay? ठीक है? चलो, let us do some questions on this. So, just write this formula, omega, in the square brackets. Write this also. This is Fermi-Dirac distribution function. This one. And if you get minus here, then what it will become?
Bose-Einstein.
Bose-Einstein. And if this becomes 0, then
Maxwell-Boltzmann.
Maxwell-Boltzmann. तो एक ही से from this formula we can get everything. Okay.
सर ए क्या बताया था डीजेनरेसी
Parameter, capital A.
ओके सर
Okay. चलो अब जरा क्वेश्चन लिखो. A Fermi-Dirac gas has two particles. No, sorry. 8 fermions is to be adjusted. 8 fermions is to be adjusted in one-dimensional harmonic oscillator. One-dimensional harmonic oscillator. Eight fermions is to be adjusted in one-dimensional harmonic oscillator. Calculate ground state energy. Okay. 8 fermions are to be adjusted in one-dimensional harmonic oscillator. Calculate ground state energy. Do it. Hello. So one-dimensional harmonic oscillators energies are like this. En is n plus half h cut omega. So this will be half h cut omega 3 by 2 h cut omega 5 by 2 h cut omega 7 by 2 h cut omega, like that. And if you have 8 fermions, you need A, like that. 1, 2, 3, and 4. So it will be A, 1, 2, 3, 4, 5, 6, 7, and one more. Let us make 8. 1, 2, 3, 4, 5, 6, 7, 8. So this is the system, and the ground state energy of the system will be equal to half. So you can take h cut omega common, h cut omega by 2 common. So 1 plus 3 plus 5 plus 7 plus 9. 1, 2, 3, 4, 5. plus 11 plus 13 plus 15. 1, 2, 3, 4, 5, 6, 7, 8. So 8 fermions are arranged. Right? So this will become h cut omega by 2 into कितना हो जाएगा? 2a. What is how to add this? N by 2 into 2a plus n minus 1
N minus 1 into D.
into d, which is common difference.
सर तो ये फॉर्मूला एक बार बता दीजिए.
Sum of n terms of AP is n by 2, 2a plus n minus 1 times d, which is common difference. So n is 15.
15 कैसे
सर
होगा?
N15 कैसे आया?
Oh, sorry.
n तो 8 होगा ना.
1, 2, 3,
And
4,
8 होगा,
5,
sir.
6, 7, 8. It will be 8. And here also 8 minus 1. 8 minus 1. Okay. First term is 1. So it will become h cut omega by 2 into 4 into 2 plus 14.
32 h cut omega.
So 32 h cut omega. Okay. And ठीक है, समझ आ रहा है? Everybody is able to understand?
सर
And in second question, if I take 8 electrons, then it will be AA, 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 and AA. So it will become, the ground state energy will become 2 times h cut omega by 2, 1 plus 3 plus 5 plus 7. So this is 16. 16 h cut omega. So you can see, if you have electrons, because every state will become doubly degenerate, corresponding to spin half, right? So 2 electrons here, 2 here, 2 here, 2 here. So 8 electrons will be accommodated up to here. And your ground state energy reduces because of the degeneracy. Because now more electrons can be accommodated using Pauli's exclusion principle. More electrons can be accommodated using Pauli's exclusion principle. Clear? Hmm.
जब ग्राउंड स्टेट की बात थी तो सर हम हाफ एच कट ओमेगा पे क्यों हमारा आंसर खत्म नहीं हो गया.
What is half h cut omega?
ग्राउंड स्टेट एनर्जी ऑफ वन डायमेंशन हार्मोनिक ऑसिलेटर.
So that is ground state energy of, so suppose you have one fermion and you have been asked what is the ground state energy of this, so that is half h cut omega. So this is one particle system. one particle system. But if you have 8 fermions, so the
Yes.
system is made up of 8 particles. So you have to accommodate 8 particles. Then whatever is the minimum energy is the ground state energy of the system. So
Okay,
when you
sir.
say that ground state energy of harmonic oscillator is half h cut omega, you are talking about only one particle.
Yes. Yes, sir.
Okay. So
सर
clear हुआ?
सर ये शाम का आंसर सर ठीक है मेरा 30 का ओमेगा आ रहा है
कहाँ पे? यहाँ
नहीं इस हाँ
14 to 16
फाइनल आंसर सर फाइनल आंसर मेरा 30 का ओमेगा आ रहा है
16 and 2 8 and 8 4 ja 32. That is okay. ठीक है?
ऊपर जो समेशन का फॉर्मूला सर वो ठीक है सर
ये हाँ
सेकंड में हाँ हाँ
हाँ हाँ
ओके सर ठीक है सर मैं चेक कर लूंगा सर
Sir, electrons are fermions, no?
electrons are fermions. We have spin half. So check what we have written. Spin half particles are what? Spin half particles are fermion. So if you remember that this A, which was e to the power alpha, and that we calculated in the Maxwell-Boltzmann distribution also, the value of e to the power alpha. Anybody remembers? What was that?
सर h कट क्यूब बाय रूट ओवर sorry 2 pi m kbt to the power whole 3 by 2
E to the power alpha is dimensionless. So what was that?
Sir, N by V.
N by
V.
V lambda t cube.
Yes, sir.
yes sir yes
Okay. And this was A. And this is N by V. What is lambda t?
That is square upon under
H
root
by
m
under root 2 pi m
kBT to the power 3 by 2.
kBt to the power 3 by 2. This is it. So please see, if I draw a line like 0 here and higher values of A here, okay? So if A is very small, that means lambda t
H square.
h square. No, this is e to the power minus alpha, I guess. This is e to the power minus alpha.
yes sir
Check.
e to the power minus alpha
This is e to the power minus alpha. So if t is very small, because a is like proportional to, so if you write a, which is e to the power alpha, it will be what? It will be proportional to temperature and inversely proportional to number density. Am I right? N is equal to N by V. number of particles per unit volume. So
और सर
if
ऊपर h square होगा.
हाँ ठीक
सर
है, that will be h square. हाँ
सर फिर नंबर डेंसिटी के तो डायरेक्टली प्रोपोर्शनल हो जाएगा ना, n by v है,
it will
इक्वल
be
टू n.
wait, it will be, yes, it will be proportional to, so that means less temperature means less A.
सर इनवर्सली t के गुना,
सही लिखा हुआ है,
सर इनवर्सली था।
हाँ
और
ये
सिर्फ
सही,
टेम्परेचर के
दोनों
गुना.
सही है, 1 by n. So if you are this side, that means it is quantum mechanics when the value of A is very small, because your temperature is small, low temperatures. Let us write it so that everybody understands. Let me write it again, and then simple proportionality hai, nothing else. A is equal to e to the power alpha, which is equal to, so if you want to write here, what it will become? E to the power alpha is v by n. And here lambda t cube, correct? So it will become 1 by n lambda t cube. Is that right?
Yes
देखो
sir.
भाई सही है ना? So if temperature is low and number densities are high, then it is quantum mechanics. And if temperature is high and number densities are low, then it is classical mechanics. Because f of e is 1 upon a e to the power beta e plus 1. So if a becomes very large, then you can neglect this one and it will become Maxwell-Boltzmann, which is classical mechanics. So classical mechanics means Maxwell-Boltzmann. And here, because we are discussing fermion, here quantum mechanics means Fermi-Dirac. All right. So if this is very large, so here you see what proportionality it will give. Temperature कहाँ जाएगा? ऊपर चला जाएगा. So it will become
Yes.
t to the power 3 by 2 and number density will come down, right? So low temperature means low A and low A means quantum mechanics. And high temperature means high A, then you can neglect one, it will become classical mechanics. Right? So A is very, very important parameter that will describe a system. So A means number density and temperature. A ultimately is a function of number density and temperature. So that means number density and temperature will define whether a system should be treated quantum mechanically or it should be treated classically. Yes? ठीक है ना बात? And if you are here, suppose we are very, very close to this, and let me treat the system. So this case will be of strong degeneracy because the value of A is very small. So that is the case of strong degeneracy. So let us discuss that case. Strong early degenerate system. Obviously, it will be a cold system, very, very cold system. So T is very small. So that's why A is also very, very small. So in this case, what I am going to do is Fe, which is Ni by Gi, is equal to 1 upon A e to the power beta E minus mu plus 1. This is the situation. And this chemical potential is actually function of temperature. But when temperature is very low, we can just write it as the Fermi, as some energy that is called Fermi energy. So this will only happen when temperature is very, very small. So you can take mu as EF and your formula will become Ni is equal to Gi by e to the power beta E minus EF plus 1. This will be the formula. Okay. So when we will be writing this? When your
System is cool.
temperature is very, very small and we are taking Ni by Gi, which is Fe. Okay. So let us see. So this is 1, this is Ni by Gi, this is Fe. Now beta, which is beta kya hai? This by kBT. Beta is 1 by kBT. So you have to consider energy levels like this. Then there will be a level which is called Fermi level. And then there are another levels. Fermi level is also some energy level. Okay. This is the energy. So let us make the system like this. So if we are seeing the energies which are greater than EF, please see this. This is very interesting. Suppose we are seeing the energies which are greater than EF, then what will happen? Ni by Gi will become 1 upon e to the power some A by T plus 1. Is it okay? Where A is E minus EF and it will be positive. Can I say that? And
by KB also.
since by KBT, and since T is very small, so I can write Ni by Gi is equal to 1 upon e to the power infinity plus 1, which is 0. So that means Ni is equal to 0. Yes? Because T is equal to 0 means 1 upon T is equal to infinity. So इसका मतलब हो गया कि at 0 Kelvin, no fermions will be there above the Fermi level. Fermi level से ऊपर कोई भी fermion नहीं होगा because वहां पे देखो Ni is equal to 0 R. No fermions can be there above the Fermi level. Yes? And if you take E less than EF, then E minus EF is minus A, and A is less than 1. So Ni by Gi is 1 upon e to the power minus infinity plus 1. So Ni by Gi is 1. That means Ni is equal to Gi. That means every degenerate level will have the particles. So that means all filled. So this is all filled and this is all empty. पहले यहाँ तक समझो, उसके बाद बताता हूँ. कोई मैथ्स नहीं समझ आ रही, यू कैन आस्क.
Sir, here mu of T chemical potential, na?
Mu of t, I told you this is chemical potential.
सर केमिकल पोटेंशियल को फर्मी एनर्जी के साथ कैसे कंपेयर कर रहे हैं?
So that is another thing, that is infinite series where EF is there. If you take T very small, all those terms goes to 0. The first term is EF. Okay. So there is an infinite series containing the Fermi energy. ठीक है?
सर ए को स्पेसिफिकली लेस देन 1 क्यों लिखा है? जब E लेस देन EF है तब.
अच्छा, you want to write this? Mu is EF into 1 minus T by TF square pi square by 12 plus dash dash dash. This is how Fermi energy is written. हाँ जी, बताइए. देखो, ये समझ आ रहा है सॉटन?
यस सर.
तो अब यहाँ पे देखो, t को 0 कर दो, तो mu t, if t is very close to 0, then mu will become what?
EF.
EF. This is chemical potential depending on the temperature. So this whole I can only write when t is very very close to 0. Okay? हाँ जी, आप
Okay.
बताइए क्या पूछ रही हैं रूपाली?
सर हमने ए को स्पेसिफिकली लेस देन 1 कैसे लिया जब E लेस देन EF लेते हैं?
तो आप कोई EF मान लो 5 है और E है 3, तो क्या ये स्टेटमेंट सही है? 3 is less than 5?
यस सर. सर आ गया समझ. यस सर, एग्जांपल लेके पता चल गया.
मैं हमेशा आपको इनकरेज करूंगा कि आप दिमाग को थोड़ा लगाना है. मैं ये चीज क्यों इंसिस्ट करता हूँ, मुझे प्रॉब्लम नहीं आंसर करने में, बट मैं चाहता हूँ आप लोग भी अपने आप को धीरे धीरे करके डेवलप करो. नथिंग रॉन्ग इन दैट ना, ये एक्सपेक्टेशन
यस सर.
ठीक है, सबके लिए है. जब भी आप क्वेश्चन पूछते हो एक बार अपना भी, क्योंकि अगर अनयूज्ड रहेगा तो फिर अनयूज्ड ही रह जाएगा. वो सेंस डेवलप करनी है हमें, ताकि एग्जाम में वो हमें हेल्प करे. ओके, बट उसका मतलब ये नहीं कि आप क्वेश्चन नहीं पूछना है, सारे क्वेश्चन आप पूछ सकते हो, बट बी रेडी. मैं तो हमेशा ही आपको बोलता रहूंगा कि अप्लाई योर ब्रेन, एंड एज ए टीचर आई थिंक दैट इज माय रिस्पॉन्सिबिलिटी, राइट? हाँ जी, और कुछ? एनीथिंग एल्स? तो ये ओवरऑल ग्राफ कैसा बना? देख रहे हो कितनी सारी फिजिक्स निकल के आ गई. So if we make the system very very cold, suppose these are energy levels, this is Fermi energy level, and these are the levels above the Fermi energy level. So energy levels are there, particle हो या ना हो. Suppose ये 1D harmonic oscillator system है तो energy levels तो बना ही सकते हो ना. Particles are present or not present is another story. So below EF, every state is fully filled. Ni is equal to Gi, that one particle, one quantum state. If it is electron, then two particles, because there will be a spin degeneracy, right? So this will be all empty, and this will be all filled. So how to define Fermi energy? You have a system, just cool down the system near to 0 Kelvin, and the highest energy of the fermion will be the Fermi energy. Correct? So this is the electron having highest energy, because above this there is no electron or no fermion. So the highest energy of the fermion is called Fermi energy when your system has been cooled down to near 0 Kelvin temperature. So this is the definition of Fermi energy. Right? So if you plot the graph of Fe versus some EF, so what you will get? The value of Fe is 1 up to EF. Yes or no? The value of Fe is 1 up to EF. Up to EF it is 1, and after this it becomes 0. So this is at 0 Kelvin. This is E. समझ आ गया? And for greater temperature, if you plot the graph, it will be like this. This value will be half. This is for T greater than 0. Okay? So यहाँ तक किसी को कोई doubt है? Is there any doubt up to this? So up to Fermi energy, it is fully filled, and after Fermi energy, it is completely empty. Because Fe is Ni by Gi, you can understand. Ni is equal to Gi means every quantum state is having one particle. Okay? Okay then. We'll discuss from here onwards in next class. Thank you.
Thank you. Thank you, sir.
Thank you, sir.
Thank you.
Thank you, sir.
Thank you, sir.